Welcome back. This is Larry Benko, W0QE, and this video is about easing into SimSmith version 16.3, which was officially released last week and is available as a download from the SimSmith website. I would encourage everyone to upgrade to this version as some small things have been fixed and some new features have been introduced. I've been kind of a holdout on version 16.2 and 16.3 as far as wanting to do video on some features for a couple of reasons. The primary reason was mentioned in the previous video on the Smith chart and nothing but, where I indicated the value of being able to center the Smith chart near the area where you want to look at impedances. And in version 16.3, this feature has been added, which is a huge improvement in my opinion. Consequently, I'm completely on board with version 16.3 right now, and I will be doing some videos dealing with some features that are new to 16.3, and also that are features that negate the need to do things the way I did them in the past. So let's begin with the examples. One of the first things we might see in version 16 that's different from previous versions of SimSmith is data entry. And data entry, say for the load impedance here, would be something like 60 plus J20. And if we go and click right here, we see the impedance is 60 plus J20 as we expected. And we're capable of moving these values around if we wish. I'm just moving the scroll wheel on the mouse right now, but it's 60 plus J20. And everything internal to SimSmith is a complex number, yet we enter the data here as real numbers. We enter a real number for the real part of the impedance and a real number for the imaginary part of the impedance. SimSmith combines the two into a complex number. SimSmith now allows us to enter that as a complex number directly. I put a load generator block here. I'm going to delete the cloning of the load piece of it. So that now this can be moved without being driven from the load block. And we can put the impedance directly in here. We can put 60 plus J20 in here. And that gives us the wrong answer because there's a 20 there too. We don't need anything there. 60 plus J20 here is interpreted by SimSmith to be a complex number. And if we look at it, we see that the point is 60 plus J20, just as they're both the same impedance. To SimSmith, these two are exactly identical. Well, not entirely identical. If you had some block that was reading LG1.J ohms versus L.J ohms, it would read different values. But the value that gets put into SimSmith is the same for both cases, for the impedance here at the low of the L block and the impedance here for the LG1 block. If we can do this, that also means we can probably do some other things. Here's another case. And in this case, let's try this and see if this works. And SimSmith is perfectly happy taking this value. And what we see is, again, 60 minus J20. What this says is the real part is 0 ohms. The imaginary part of the impedance is 20. There's our J20. And plus another minus J60 times J. J times J is minus 1. With the minus sign is plus 1. So this becomes plus 60 real plus 20 imaginary. So this becomes 60 plus J20. And while we're doing that, of course, we can get a little bit more carried away. And 30 plus J10. And we can put something down here like 10 minus J30. And this should also be 60 plus J20. And sure enough, it is. And any combination. So it takes these two values, complex or real, it makes it the real value. It takes these two values, or the value in here, multiplies it times J and makes that, and then adds it to this value, and that's the resultant. This and this are not very wouldn't be commonly used. But the first one is part of this process of making SimSmith more orthogonal or regular, or however you want to think about it. But if I wanted to do the following, let's say I had a resistor here, and I wanted to make the value of this resistance equal exactly to the load impedance. There's a lot of different ways I can do that. We'll do it in the daemon block. We can say something to the effect like we used to do. We could say R1 dot ohms. So that's the field we're going to start again. R1 dot ohms equals L dot ohms, and then R1 dot J ohms equals L dot J ohms. And what we see is this field matches this field. If I change this field, it tracks. This is how we used to do it. We now can do it differently than that, and to do that, I'm just going to comment these two lines out. Where I can now say R1 dot ohms equals L dot Z. L dot Z is the impedance looking in here. And that has exactly the same effect too. Notice that this value here is kind of weird. I set this to be, this 20 is from before. We're no longer updating it, so really this needs to be 0. It won't ever get updated when I change this, but it was a holdover from it was a data value that was calculated, and that's one thing in SimSmith. If you calculate a value for a parameter field, and then you take away what was writing that, it keeps the old value there. And that's burned me a few times in the past, but it's the most logical thing to leave behind, which was what was previously there. But nevertheless, there's a lot of different ways to enter the data now, but this is a much more easy way to do it than what we had before. And it's, again, part of the process of making SimSmith more regular. The next thing that's slightly different from previous versions of SimSmith is plotting. This circuit is a pretty simple circuit. It's a 40 ohm resistor in series with a capacitor. And I've done three separate plots here. And in version 15, we would have done plot with a small p, no parentheses. Inside the quotes here is the name that we want to appear in our tab. If we leave that blank, what we would get is C1Z. C1Z is what we're plotting. We're plotting the impedance at point C1, looking this direction. And we're going to plot it on the Smith chart. And if we look at that, what we see is exactly what you'd expect. We started 40 ohms here. This is the case at the highest frequency where we have the minimum reactance in series for the capacitor. And down here is where we have the most reactance for the capacitor. And there's the arc that we get. In version 16, this formula still works, or this construct still works just fine. However, the preferred method of doing it is this way, and all new features for plotting will be made to work in this structure and may or may not work in the old format. But the new format is P with a capital P, plot with a capital P, parentheses, and inside it is what we're plotting. Again, here it's example 2. It's the same thing we're plotting, and Smith is in parentheses. If we look at that plot, we see it's exactly on top of the last one, so it does the same thing. And as a shortcut, when we do this plot, we have the choice of putting any of the 5 plotting axes that SimSmith has as the destination for where we're going to plot. We could plot on the power scale on a square chart, the SWR scale on a square chart, a new axis small y1 over here, which you can label to be whatever you want it to be, and another axis over here, y2. And then the fifth axis, of course, is the Smith chart axis. And this version right here is just a shortcut. And so we use the word Smith instead of plot, and it tells us it's a plot command that goes to the Smith chart. If we look at that one, we see again exactly the same. The documentation describes these two ways of doing it, does not indicate that this even exists anymore. It does work. So there's no backwards compatibility problems, but the current format is this way. And I believe there's some new plot features either that are not compatible with this version right now that exist, or there will be. But any new features won't work with the old version. So I would encourage people to start plotting this way. It's not that much different. It was done for some reasons of being able to parse what was in here. There were some cases, I think, where the parsing was ambiguous. And anyways, this clears a lot of that up. Now we get to a new feature that's in version 16. And it is, again, going down the road of making SimSmith more regular. And what I've got here is a circuit which I'm doing this all in resistors and resistances because resistances are easy to do the math in our head. A 40 ohm load, a 10 ohm resistor we're going to call component 1, a 5 ohm resistor we call component 2, a generator with 50 ohms. Now, there's lots of things we can plot here. The first thing we can plot is L, the impedance, and turn that one off, okay. And L, let's look at the plot window here. I left these three examples from the previous, let's just get rid of those. That was from the previous example. And here's what we're left with. We're left with these things that I've chosen to plot here. But for the moment, let's look at the old things we could plot. We could plot L. L really was exactly the same as plotting L.Z. And I should probably do that just to show that. We'd say Smith, and then we'd do L.Z, and we would be done. So there's L. You can see the X going away. Here's L.Z right on top of it. And these old plots that came from, they were just default, and everybody sees them without writing anything, with the impedance looking at the individual points looking to the left. So L is the impedance, turn that off again. L is the impedance looking from here to the left, which is 40 ohms. If we click on CMP1, we see 50 ohms. The impedance looking from here to the left is 40 plus 10. If we go to CMP2, we see that is 55 ohms, and that's 40, 50, 55 ohms. So there's nothing new there. Now what is new is, if I can look to the left, it'd be nice to be able to look to the right. And that's kind of an interesting concept. So again, if we go back here and look at the plot window, the reverse function, REV, Z, as opposed to just Z, is looking to the right. So we have a Smith CMP1 REVZ. This right here, looking to the right. Let's see what that gives us. So that's right there. That shows us 65. Did I click on the right? I'm sorry, I clicked on the wrong one. There we go. 55 ohms. I'm not quite on it exactly, but 55 ohms. So 55 ohms is what we see when we look from here to the right. If we look from here to the right, which is what I clicked on initially in error, that was L.REVZ, we see 65 ohms. 50, 55, 65. We're looking here, we're looking to the right. Kind of interesting. We can look right here at CMP2 to the right. And what do we see? 50 ohms. So we're looking here, we're looking this direction, and we see the generator impedance. Now, why would we want to do that? Your guess is as good as mine. There are cases when it's kind of nice to know, although as far as solving problems with it, it's probably less valuable than looking to the left. However, along the lines of the REV reverse Z feature are the inverse Z feature. Now, the inverse Z feature is a feature that I have not mentioned in version 16, and it's a feature I didn't like. I didn't like it for a couple really good reasons, but it's now been fixed. And it's been fixed to the point now that it is really cool. And in the video, 2 videos ago when I was talking, or maybe just 1 video ago, I was talking about the center of the Smith chart being important whenever you look at stuff. We used to not be able to do that, but we controlled where the center was initially. Now we can control where the center is exactly. But for this purpose, we're not going to mess with the center of the Smith chart. We're just going to see what it does. When I look at, turn all these off, and I'm going to turn on just one of these. And L dot inverse Z gives me a value of 35 ohms. I'm having a hard time clicking on these exactly, but it's 35. So 35 ohms is the impedance here that would give me a match back here. So we're looking this direction sort of to make the impedance as far as what we have a match, but we're doing a calculation so that we know that we're going to get the match here. So when I used to do this, I used to start here and I used to negate the components going this way. Now we're going to look here and just say what the value is to give me a match. 35 ohms plus, so 35 ohms here. Don't think of this as 40. Whenever we do this feature, we're saying what value does it need. So down here again, L dot I and VZ. What value needs to be to the left of this? It doesn't have to be one component, it can be several components. What value to the left of this is such that when I take the circuit to the right, included on top of the value to the left here, I get the correct impedance here to match the generator. So 35 ohms, 45, 50. We're good. Let's look at let's look at CMP1.INVZ. That says, what impedance to the left of this point, CMP1 point right here, what impedance to the left of this would give me a match to the generator? Well, the number we see here is 45 ohms. So 45 ohms to the left of here, plus the 5 ohms, gives me 50. Pretty cool. So now we can do something else if we wanted to. We could say, what impedance would I get if I was to put an ohm meter from here to ground? That would be the impedance looking to the left, and that would be in parallel with the impedance looking to the right. And what I did is I did a formula down here. The impedance looking to the left is CMP1.Z. The impedance looking to the right is CMP1.reverse Z. And it's 1 over, 1 over, 1 over, which is the formula for being in parallel. And I click on that value, and now I see 26.2 ohms. And if we take 10 plus 40, which is 50, 50 in parallel with 55 ohms, we get something like 26.2 ohms. I think actually we get 26.2 something, 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 but this only shows it to 1 decimal place. But that gives us the impedance. So if you wanted to debug a circuit and you want to just put your ohm meter to ground, like some of the old debugging manuals had for TVs and stuff, they didn't want you to break the circuit. You just measured an impedance at a point. This can measure the impedance looking both directions at the same time. But nevertheless, this is some really powerful stuff. With the ability to look in any direction you want to look. And the inverse Z function and the reverse Z function are both new in version 16. And with the addition of a couple other parameters, which I'll talk about in the next video, these features totally negate the value of what I used to do. And to finish up, one final little circuit that's kind of interesting. We have a component called Xmatch, and the Xmatch component varies its output impedance such that it always produces maximum power into the load. But now that we can look to the right, we can look and see what the impedance of that generator is. So here we have a case where we have it's a 100 watt generator, Xmatch times the power variable, and power is set to be 100 watts. And when I have a 50 ohm load in the output, I get 100 watts out. Now if I can, shouldn't have changed there. 100 watts into the circuit. As I change the impedance, notice how the X match changes so that I continue to see 100 watts here all the time. No matter what the impedance is, I see 100 watts. Let's now look at the impedance. We know the impedance right here looking to the left. Let's plot that though. The impedance looking to the left will be L. It's L. Or L dot Z. That's looking to the left. That's 50 ohms. The impedance looking to the right would be the reverse. L dot REVZ. L dot in the reverse direction. And there it is right on top itself. Now, as I change the impedance here, look what happens. The two track. So when I have a 40 ohm impedance here, the generator looks like 40 ohms. What if I have a 40 plus J20 impedance here? Now my generator impedance becomes, so 40 plus J20 is right here. 40 plus J20, roughly. My generator impedance becomes 40 minus J20, which is a complex conjugate of what the load impedance is. And that's exactly how you get maximum power transfer. And that's kind of a cool experiment. Just be able to move these around. Now there is one downside that I didn't mention earlier, and I can just demonstrate it here at the moment. But if I had put my impedance in here directly as a complex number, if I go up here and I scroll the mouse wheel, what would you expect to change? This value, or both? It turns out we changed just the real part. I don't know that that's something that will stay with SimSmith or not. It may change in time, but it's ambiguous. If you intend to scroll these fields, you're probably better off leaving a real part and an imaginary part to scroll independently. But nevertheless, this is just, this is some insights into how to use version 16 and some of the new stuff that's available in version 16. In the next video, I was going to talk about the very last time I'm ever going to mention it again with the negative components, negative circuits in a backwards direction to calculate what impedance a network will match to. I'm totally on board right now with the new version 16. So hopefully that video should be shorter, I hope, and hope you enjoy it and hope you enjoy this video. Thank you very much.